Alright, the last paper of the session is called Rapid Visualization of Geological Concepts. It's by people from Bergen in Norway, and Mattia Natali, who is a PhD student working with Daniel Patel, is going to give the talk.
Thank you for the introduction. My name is, good morning, my name is Mattia Natali, and today I will present this work. Is called Rapid Visualization of Geological Concepts. It was made in collaboration with Ivan Viola and Daniel Patel. Okay, the aim of this work was to create the 3D illustrative models that you can find in geological textbooks. For example, you have such a model here in the bottom, where they wanted to show the stratigraphy of the terrain with these 3 layers and a fault in the middle. And this is a way for geologists to express and explain processes involved in the subsurface. And we want to achieve this exploiting the sketch-based interface to rapidly obtain geological illustrations. I will introduce structural geology, that is the study of the 3-dimensional distribution of rock units with respect to the deformational histories, and it can be shown for teaching purposes, like the example on the right, on the left side of the slide, or it can be used for communication between experts. If someone wants to explain something that is happening in the subsurface and want to show to someone else, he has to he can exploit such a structure to give the idea. And this is something that is called visual thinking. And this is the importance of communicating an abstract idea. And these geological illustrations are expressiveness, so are expressive. That means that we try to avoid many details, and we keep it simple, and we just want to show the concept of the model. As I said, we show and explain how the Earth has behaved or will behave in the subsurface, and these geological illustrations are also self-descriptive, because you can add some notations or some arrows to convey the movement of these blocks, and usually you find also some labels explaining what is happening. And why we use a sketch-based technique? We use that because it's intuitive also for non-experts, and by non-experts we mean geologists who are not illustrators, that are not artists. And a sketch-based technique that does not require many hours to build the model, because we can replace all the parameters and all the details with freeform sketches. And we want to cover the need for a rapid modeling tool, because it's missing in the geological field. In this slide, this parallelism with architecture and geology. And in the case of architecture, you have programs that can build almost everything for example in the of a house, but when you have to show only the concept and you want to do it in few seconds, you have to use another tool that is in this picture is SketchUp to build the model in few seconds and just communicate and convey the concept. And this is missing in geology, because you have such programs that can build a very detailed model, specifying all the details and all the values of each surface. And we want to fill this gap, having this such a tool for sketching in with few strokes the concept. As I said, this is the combination of the two tools, the sketching tool and the geological illustration. And what we can achieve is this 3D model. That is, on the contrary, this is just an image. With our tool, we want to get a 3D model that can be used, can be assessed with the interaction from the geologist. And geologists usually are dealing with such sketches where you can find, they define some horizons, the fault here, you find some notation giving the movement of the fault, and the labels for the type of the rock they want to represent. We want to get such sketches and build a layer cake model. In such sketches, geological sketches, you usually find fold and faults. A fold is the formation of an original flat layer, usually produced by a sedimentation process that has been bent by forces acting in the crust of the earth. On the contrary, a fault originates when forces that act on a specific layer are so strong that they overcome the rock's elasticity and yield a fracture. And in the case of a fault, you can distinguish between the hanging wall and the foot wall, that are these two blocks in the bottom, and you can derive them knowing the inclination of the fault trace. If the fault has this inclination, the hanging wall is always on the left side. And we want to keep this tool as simple as possible. Starting from a definition of a fold with just two sketches. The user sketch these two strokes, and you get one layer of the layer cake model. And if he wants or she wants to define a fold, you just need to add another stroke, red in this example, and he will get a fold in the final 3D model. There is another property that is useful if you want to convey erosion instead of just folding, because in this case you get a deformation of the texture on the basis of the shape of the boundaries. But if you want to convey erosion here, you have to sketch the shape of the layer This is the description of the entire process, starting from starting from scratch from a white canvas. You get the sketches from this view that is called a cross-section view. Each sketch is extruded as a surface in the other dimension, and the horizons are put together to form each layer, and each layer is a kind of rock that will be given a kind of texture conveying the type of the rock. Then there is the guide texture if you want to change the shape of the texture, and finally you can add some drawings or notations, and this is the only part where the sketch is not done in 2D but directly on the 3D model. And how to define the fold. Each layer is acquired as a set of points. Each layer is defined by two curves. Each curve is a set of points. This set of points is triangulated with Delaunay triangulation, and this Delaunay triangulation is constrained because otherwise we will get the convex hull of the sets of points. After we get the first and the coarsest triangulation, we will refine the mesh. For example, with a 1 to 4 triangle refinement, and we will apply the texture on this geometry with a conformal map, and I will explain how. For defining a fold, instead, we need to have a layer defined from before. We sketch the fold trace in red in this picture, and we define a vector that is the displacement of the two blocks moving because of the fold. And each curve intersects the fold trace here in the point PIK. The point PIK moves along the fold, and this movement will generate a vector that is the displacement vector that will be applied on the entire piece of curve, and will move the block that in this case is the hanging wall. After that, we can apply texture on each block of the fold. The texturing is made by a conformal map, and this is why because the conformal map can maintain the expressiveness and the meaning of the texture, and usually textures are of this kind. You find in textbooks and illustrations some this kind of textures, and the conformal map by definition is it preserves the angles, and we do it by minimizing a functional that takes in consideration all the angles from the domain and the image space of the texture. When we have the texture on the layer, we can guide the texture and finally put some projected drawings. The guided texture works as following. You start with the original two curves defining the layer. and you sketch one stroke here in blue to change the shape of the texture to get something like in the final image. After you acquire the blue sketch, you make a copy of it and you place it above the first curve and of the lower curve. You apply the conformal map on the external boundaries, and you extract what you need from the inside of the original two boundaries. Those are some results with this technique. The first one is with some examples of a folding process and the fold with two arrows conveying the movement of the fold. There is an example with a more illustrative texture in the bottom right, and one example including every options with the guided texture in the layer in the middle, and the fold, some drawings, for example, for salt domes, and other examples in the next slide with a multi-fold example, and an oceanic crust on the right, with that is conveyed by just simply put some transparency in one of the layer, in the top layer. The comparison is made with the state of the art of illustrators. Nowadays they use Adobe. This is a special case, but he uses Adobe Illustrator to make such illustrations, and at the end you will get just a picture of it. And just for making the first example, he said that he would employ a full day. On the contrary, with our tool, you need only a few strokes and define for each layer the corresponding texture, and you can do it in a few minutes. The same will happen with the other two models, and he would employ less time, because he said that in these examples the texture doesn't follow the boundary, and it's also less photorealistic than the example in the top. As a conclusion, I can say we show the sketching tool for a specific domain, and with just two operators that are folding process and folding process, we are able to cover larger amounts of situations that you can see in textbooks. And with the guided texture, you can also add some erosion. It is fast and intuitive for the user, and you can use it for generating this illustration. This on the bottom is a comparison with an illustration from a textbook, a geological textbook on the left, and a model acquired with our tool. Of course, there is a lot of space for future work, and we thought about widen the model with more geological events like salt domes, deltas, and channels. And we thought about providing physical simulation like erosion or fluid flows, especially in the top surface. And we also tried to animate these illustrations, and this is a work that is in progress, is almost at the end. And finally, as suggested also by a reviewer, impose some geophysical concepts. And with that, I would like to say that this work is part of the GeoIllustrator project, and you find in the last slide the references. Thank you.
We have time for questions.
In that last model, you showed the comparison with that illustration, that one. How do you author the overall sinuous shape of the crests of the mountains? Because it seems to me that you only extrude from a 2D. Yeah, just going on. Yeah, and how about the Oh, just the illustrator actually drew that.
Yes, the surfaces are just extruded, and this is
There's some details made up by hand.
Authored by the user.
By hand.
By hand.
Okay. I'm going to ask you about the salt domes, but since this is future work, then I'm not gonna ask that.
The salt dome can be done, but the geometry would be incorrect. Because you can define a salt dome here, but then it will be extruded, just extruded, and the model. Radio. Yeah. Radio. Yes.
Hi. Have you tried to use a real seismic data to create the illustrations or your models?
The aim of this tool is to get the model from scratch, but
because it seems to be possible.
The user could use some seismic data as a background, and then sketch on the
draw over the seismic.
Yeah,
but have you tried that?
Just with the I tried with this one.
Thank you.
Any more questions? Okay, if not, testing the speaker again.